In this presentation, we'll talk about electromagnetic waves, and we'll focus on the electromagnetic spectrum. So electromagnetic waves are another classification of waves. So we've talked about mechanical waves, which need a medium to travel through. Electromagnetic waves, on the other hand, do not need a medium to travel through. They can actually travel through the vacuum of space. Electromagnetic waves are transverse waves, and these waves still have the same properties as all mechanical waves. There's a certain frequency associated with electromagnetic waves, a wavelength. Electromagnetic waves travel at a particular speed, they have amplitude, they can be reflected, they can be refracted, they can have interference, and they can also have diffraction. So basically everything we talked about with mechanical waves are also possible with electromagnetic waves. It's just that those electromagnetic waves do not need a medium to travel through. It turns out that visible light is one type of electromagnetic wave, and so we're going to talk a lot about visible light and some of the properties of visible light. We'll also talk about some of the other types of electromagnetic waves. Light actually has a dual nature associated with it, so it behaves as a wave sometimes, but it can actually also behave as a particle. Just mentioning that, we're really not going to talk about the duality of light, but you may have heard that term before, so just be aware that light can behave in more than one way. So we can ask the question, what is the vibrational source for electromagnetic waves? Because we know that all waves have some source of vibration. And it turns out that what produces electromagnetic waves is a charge that is accelerating, that's oscillating rapidly. And in this particular case, actually, as long as the charge is accelerating, it doesn't have to be oscillating, but typically electromagnetic waves come from oscillating, accelerating electrical charge. So to show this, there's two PhET simulations that sort of go through this. So I'm going to pull those up. First, I have a picture here of an electrical charge. It's a positive charge. And and right now this is showing the electric field, which is pointing away from that positive charge. So I can oscillate this charge, so I can manually do that, and I can go like this, and that causes those electromagnetic waves, or it causes the electric field to oscillate in time. And when you have an oscillating electric field, that also causes a magnetic field. So this oscillating charge here is actually producing an electromagnetic wave. So I'm going to go ahead and I'm going to hit sinusoidal, which will cause that to oscillate. And what you're seeing are these electric fields which are oscillating in time, and that will produce an electromagnetic wave. Let's stop the charge from moving, and let's look at another simulation of an electromagnetic wave. So this is also a PhET simulation. In this particular case, you have an antenna, which is a source, in this particular case, of radio waves. So this is supposed to represent a particular radio station, KPHET FM 98.7, and on the antenna is an electron, or there are electrons in there. And what happens is that if we oscillate those electrons, it produces an electric field, and it also produces a magnetic field. Now in this particular case, this is more or less showing the electric field in the picture, but what happens is that that field spreads out and it travels along, and then over here is a house, and there's an antenna at the house, and it's picking up that electromagnetic wave signal and causing another electron in that antenna to oscillate up and down and pick up the signal. So in both cases, you have to have some accelerating charge that produces the electromagnetic wave. So all electromagnetic waves are made up of a vibrating electric and magnetic field. And the electric and the magnetic fields are always in phase with one another in the sense that they're both maximums and minimums together. And they're always perpendicular to one another. So in this particular picture on the right that shows an electromagnetic wave, I have the blue lines here that represent the electric field, and at a given time, that field strength is oscillating in time, so the electric field is increasing, decreasing, changing direction, increasing, decreasing, changing direction, and at the same time, the magnetic field is increasing, decreasing, changing direction, and what we notice is that they are maximums together, and they're always perpendicular to one another. The other thing that's true about electromagnetic waves is that the wave direction, the way that it travels, is always perpendicular to the direction of both of the fields. So in this picture, I have a three-dimensional coordinate system. My magnetic field is oscillating about the z-axis. My electric field is oscillating about the y-axis. And the wave is actually traveling along the x-axis, which is perpendicular to both of those directions. So electromagnetic waves come from a vibrating source. That vibrating source is an electron or charge that's accelerating or vibrating, and it produces these electric and magnetic fields that make up the electromagnetic wave. So there's some interesting videos out there that you could take a look at that sort of describe electromagnetic waves and the electromagnetic spectrum. And I would sort of urge you to take a look at these, but I'm not going to show the video inside of a video, but there's a great one. I think the first one is actually really very relevant and a great video to watch. So since electromagnetic waves are waves just like any other wave, they travel at a particular speed, they have frequency, they have wavelength, and so on. So electromagnetic waves are different than, say, waves on a string or waves in a column of air because all electromagnetic waves travel at exactly the same speed in a vacuum. So in the vacuum of space, out in space, every single type of electromagnetic wave travels at exactly the same speed. And that speed is called the speed of light. And so we give it a special symbol, c, for the speed of light. And the value for that speed is 3 times 10 to the 8 meters per second, or 300 million meters per second. A common misconception is that electromagnetic waves travel at different speeds, but they all, regardless of what type of electromagnetic wave you have, they're going to travel at exactly the same speed. So we could ask the question, if all of these waves travel at exactly the same speed, then what makes one electromagnetic wave different from another electromagnetic wave? And the answer is that we know that the speed of a wave depends on the frequency and the wavelength. So the speed of any wave is frequency multiplied by wavelength. So even though they all have the same speed, electromagnetic waves will have different frequencies and different wavelengths with respect to one another. So we can characterize electromagnetic waves by their frequency and their wavelength. So here we have a picture of the electromagnetic spectrum. And the way that we could read this is that on the left side of this picture is frequency of the different electromagnetic waves. So at the bottom, we have low frequency electromagnetic waves, and at the top we have high frequency electromagnetic waves. And since the speed of the wave is constant, we know that frequency and wavelength are inversely proportional to one another. So an electromagnetic wave that has a high frequency will have a short or a small wavelength, and an electromagnetic wave that has a low frequency or a small frequency will have a large wavelength or a long wavelength. So the range of these electromagnetic waves in the spectrum range from radio waves, which are very low frequency and very long, up to very high frequency gamma rays, which are very short in wavelength. So you'll notice in this picture that we also have the visible light spectrum right here. And we've had to blow up this particular part of the spectrum because it makes up a very small portion of the entire electromagnetic spectrum. So we're going to talk a little bit more about specifically visible light, and also, what's the big difference between something that has a high frequency and a low frequency. But since all of these electromagnetic waves travel at a constant speed, we can figure out that what the frequency is based on the wavelength, or we can figure out the wavelength based on the frequency. So there's this inverse relationship that I mentioned before, and anything that has a very large wavelength, which would be radio waves, will have a very small frequency because they are inversely related to one another. So electromagnetic waves are basically classified according to their frequency, and I wanted to sort of point out that these regions are not sharp boundaries in terms of where one type of electromagnetic wave ends and another type begins. So we notice that here are gamma rays, which are our high frequency electromagnetic waves, but they overlap some with X-rays here in terms of their range, and even ultraviolet overlaps some with X-rays, and infrared and microwaves overlap, and so on. So there's not this sharp boundary between electromagnetic waves. One thing that is important is that the higher the frequency of the electromagnetic wave, the more energy that that particular wave carries compared to the lower frequency electromagnetic waves. So in terms of our electromagnetic wave spectrum, the top here has the highest frequency, so gamma rays carry the most energy and radio waves carry the least amount of energy. We know to some extent that X-rays actually carry quite a lot of energy, because if you've ever had to get an X-ray, the doctors or the radiologist or whoever is taking the X-rays is always concerned about how much radiation, how much of that electromagnetic wave is actually getting to your body, and so they'll often have you cover up parts of your body with sort of this really heavy I don't want to say a coat, but the sort of a covering, and it has in it, it's heavy because it's going to stop those electromagnetic waves. So let's talk just for a couple minutes about visible light in the electromagnetic spectrum. So we could talk about what the properties of the electromagnetic waves actually represent. And so when we're talking about visible light, the wavelength and the frequency tell us something about the color of the light. The frequency is always going to tell us something about the energy. The amplitude of our wave is going to tell us something about the brightness. How bright is that light, or what is the intensity of that light? It turns out that human beings, their eyes only chemically respond to wavelengths that are between 400 nanometers and 700 nanometers in length. 1 nanometer is a very tiny unit of length. So 1 nanometer is about 1/1000th of a meter. Can't even imagine 1/1000th. Taking a meter stick and then breaking it up into like a billion marks, right? We can't even imagine what that is. But 1 meter is essentially a billion nanometers, or 1 nanometer is 10 to the minus 9 meters. So we're talking about extremely tiny, tiny measurements. So our eyes do not respond chemically to wavelengths that are shorter than 400 nanometers, and that's called the ultraviolet region. And anything longer than 700 nanometers is in the infrared region. Ultraviolet light actually does come from the sun. It carries more energy than visible light, and that's what can cause sunburns. So it has lower wavelength, but it has higher frequency and higher energy than visible light. We just can't see it, but it's still there, and it's still bombarding the Earth, as is, there's also infrared. So we learn at a pretty early age the colors that, you know, are sort of the traditional colors, and I don't know if they still teach this in school, but the Roy G. Biv is how I remembered the color scheme, which is red, orange, yellow, green, blue, and then there was an I for indigo, and then violet. And so learning those colors in that order tells us the order of the colors in terms of their wavelength. So red has a wavelength that's around 700 to 630 nanometers. So red has longer wavelength, larger wavelength, and therefore smaller frequency, lower energy. And as we go down the spectrum, violet has shorter wavelength, but has higher frequency and thus higher energy. And so here's another picture of the visible light spectrum, and we can see sort of the frequencies here in the wavelengths, more so the wavelength, right? So these are shorter wavelengths in terms of measuring between crest and crest, and as you get to red, there's longer wavelengths over here. So visibly speaking, we can see ranges from around 400 to 700. And actually, you know, everyone's a little bit different. So I have a lot of trouble, for example, seeing in the violet range. So some people might have a different cutoff in this range and may not be able to see quite the colors that everybody else can see.